This problem asks us to find the work integral for the curve here that is the intersection of the paraboloid and the plane. Now it tells us to do this Stokes theorem, but somebody asked me about doing it directly, so I'm going to show you both ways. It's an interesting problem actually. So let's do it directly first. If so, then we need to parameterize this curve. And that's the part that really the person asked the question on, is that's kind of a different sort of curve than we've parameterized before. It's a little bit challenging. So we have that z equals x. So at first glance, it would seem like let's make those both t. But then we need y in terms of t. And so to do that, I would need to take a look at this equation here, the paraboloid, and figure out what y would have to be in terms of x and z. And that's where it gets a little bit difficult, because we would have y squared equals z minus x squared if I'm solving here for y. And then y equals plus or minus radical z minus x squared, which then would be plus or minus z equals t and x equals t, so we'd have t squared. And that's not ideal to have a plus or minus. And when we saw this way back when, I think we did a little bit of this in 13.1, not much. But when we saw a plus or minus, we generally tried to work around that somehow. I at least didn't see a way to work around that. Maybe there is, maybe you'll come up with it and tell me. But what we have to do then, if we have this plus or minus, is we're going to have to break this into two pieces. We're going to have to break this into the part where y is positive and y is negative. So where y is positive on this part of the curve here, and y is negative on this part over here. Now, to give you a little bit better idea what that looks like, I put this on GeoGebra and rotated around a bit. Let me show you. So there's our surface, and you can see the curve of intersection in black. And this is what it looks like looking down. This would be the projection. So you can see that would be the projection in the XY plane. Then if we look at y equals plus or minus, what we're doing is we're breaking the curve into this piece here. Well, if I color code it the way I did up there on the surface, it's this piece. That would be the plus. And then it's this piece. That would be the minus. So if we're going to do this problem directly, we'd have to break down our curve, which is this whole thing, into a piecewise defined curve. So we'll have to do C1 and then C2. So that's what we'll do first, C1 and then C2. So here's that image again. The part where y is positive is here, the part where y is negative on the left here is here. And we're told that it's counterclockwise as viewed from above. So I'm actually going to do the C2 first. So this is the parameterization for C2. And we are looking at x goes from 0 to 1. Then that means my parameterization is t goes from 0 to 1. Now, how did I know that? Where did that come from? Good question. I used my picture here, my graph. This is 1/2, so this is 1. But of course, we're not going to have the picture. We're going to have to figure this out ourselves. So I need to figure out how I knew that that was, I mean, it's not obvious from this parameterization that it's some sort of circle, and it's not obvious at all that it's this 1. So I'm going to take a minute to sidetrack here and just talk about what is that projection. Because whether we do this directly or using Stokes' theorem, we're going to need to know that. The projection in the XY plane, we'll have to take our two surfaces and eliminate z. So I have z equals x squared plus y squared, and I have z equals x. I want the projection in the xy plane, so I'm going to eliminate z, I'm going to substitute this here and get x equals x squared plus y squared. Now that's a circle, but it's not centered at the origin. I know that because of this x. So if I'm going to put this in standard form, x squared plus y squared, I'm going to subtract the x. I'll get 0. X squared minus x plus y squared equals 0. I'm getting ready to complete the square. So I take half of this and square it. So that's 1/4. And I add that to both sides. To give me x minus 1/2 quantity squared plus y squared equals 1/4. So this is a circle, and the center is 1/2 0. One more time. 1/2 0, and whose radius is square root of 4, or 1/2. And that is actually what we see in the picture. This is 1/2 0 right here, and the radius is 1/2. When I said that for the green graph then, x goes from 0 to 1, radius, center is 1/2, radius is 1/2, that's the point 1, 0. That's where I got that from. Now, we'll come back to this in just a little bit, so you kind of look back, we'll look back at this in a minute. Okay. So looking over here once again now, we'll focus on this. We need f dot r prime, so we're going to put these values in for x, y, and z in our function, and we're going to take r prime and we're going to dot them. So here I have done all that work for C1, the green one. And you can pause and take a look and follow. I'm just putting each of these in for x, y, and z, and then r prime would be 1 and the derivative of that in 1, and I dot it and I simplify it. Here's what I get. So the work done over that curve is this integral. So again, you can pause and check that out. But once we get to this integral, that's easy, that's easy. This is a little more complicated, and you can do this. We can do it by completing the square and using trig substitution. But before I bother with that, I'm going to set up the integral for the other curve, because sometimes there are terms that subtract out if it happens to be the same limits of integration. So I'm going to wait on that. Let's go ahead and look at C2. Or I guess this is what I called C2. So let's go look at C1, the blue curve. This is the parameterization for this curve, except for this time we have x going from 1 to 0, from 1 to 0. So t would go from 1 to 0, and we don't usually write it that way. We don't usually write from 1 to 0, just because it's implying that 1 is less than 0. So it'll end up working, by the way, but oftentimes what we'll do is we'll say t goes from 0 to 1, and that is actually the reverse direction. So I'll have to take the minus in the end to get it going the way that it's supposed to go, which is this way, right? If you wrote 1 to t to 0, it will work the same. It's just not mathematically correct. Okay, so I'm going to put them in just like I did on the last problem and see what happens. Why don't you pause and do the same? Again, here's the f, and here's the r prime. And if you do it side by side with the one you just did, you see that it's very, very similar, except for this had a minus, and so it affects some of these terms down here. So 0 to 1 of f dot dr looks like this, which if you compare it to the other one, it's hopeful, because the terms are similar but some different signs, so it looks like that troublesome term is going to maybe drop out. But we have to remember that the way that we parameterized it, it was going this way, 0 to 1, but it's really supposed to go the other way, so I'm going to have to take the minus of that. If I do that, I get 0 to 1 minus t cubed plus 1/2 t minus radical t minus t squared dt. Then rather than integrate each of them separately, I will take and put them together and then integrate them. So I'm going to get my C1 and my C2 and put them together and then integrate them. All right, so this is the one we just found. This is the previous one. And then we will add them together and then integrate. So these will subtract out, as will these, but unfortunately the hardest term is not going to subtract out. We're going to get 0 to 1, negative 2 of those. So we're going to need to integrate that, which is fine. It's good practice. But at least it's kind of boiled down to this. So this should give us the answer. All right, so now we check your integration skills. This is one where we can do by completing the square. You may have some other way. You may just grab the computer and let the computer do it at this point. But I've come this far. I'm gonna power my way through it. So what do we get here? We get negative 2, 0 to 1. And I want to write this as a perfect square. So I'm going to factor out the minus, and I'll get t squared minus t. And I need half of this squared, so plus 1/4, to make a perfect square. And since I have contributed a minus 1/4, then I need to add 1/4 to compensate. Again, in case you're completing the square skills are rusty, I've got a minus 1/4 plus a 1/4, which is 0. So that means I haven't changed the expression. Then this would become 1/4 minus t minus 1/2 squared. All right, you know what to do from there? Maybe not. Maybe not. Let's try some more. We've got the difference of squares with the variable part coming second. That means it's a trig substitution using sign. So I'm going to let t minus 1/2 equal the square root of this times the sine of theta. So 1/2 sine theta. Now you might have learned how to do this by first doing a u substitution and then going from there. All right, then dt would equal 1/2 cosine theta d theta. Making that substitution into here and then simplifying. Go ahead and give that a shot. So t minus 1/2 is 1/2 sine theta. So I have that squared. 1/4 dt is 1/2 cosine theta d theta. Right there. Oops. So go ahead and take the next step. Okay, here's what I have so far. You can follow it through. The 1/4 comes out as a 1/2. The 1/2 multiplies out with the 2. 1 minus sine squared is cosine squared. So I end up with a cosine times cosine, so cosine squared. I integrate cosine squared, which is 1/2 theta minus 1/4 sine of 2 theta. Okay, maybe take a minute to digest that. But I left the limits of integration off here because you can handle these two ways, right? We can change the theta's limits, and then right here we'd evaluate it. Or on these, a lot of times with trig substitution, people will go ahead and put the t's back in here and then go ahead and use t's limits. So either way you want to do it is fine. All right, it can be done either way. I'm going to go ahead and put the t's back in and evaluate add t's limits. And you do it your way, and we'll see if we get the same answer. Yikes. Okay. Not so sure I did this the best way possible, but I'm not going backwards. So here it is in terms of theta. I write the triangle or the ratios that go with it. So here t minus 1/2 is 1/2 sine theta, which means that t minus 1/2 divided by 1/2 is the sine of theta, which means theta equals the inverse sine of that. So theta here equals the inverse sine of t minus 1/2 over 1/2. Okay, and the sine of theta is opposite over hypotenuse, so t minus 1/2 over 1/2. Using the Pythagorean theorem here, this side is the square root of this side squared minus this side squared. So sine of theta would be opposite over hypotenuse, and cosine theta would be adjacent over hypotenuse. And I don't recall if I said, I don't think I did, but we need this in terms of theta because our information is in terms of theta. So I applied the identity sine of 2 theta equals 2 sine of theta cosine theta here. So this one might have been easier to evaluate in terms of theta. You can give that a shot. But I'm going to go ahead, I'm not going to show you all the steps. I'm going to go ahead and evaluate this, make sure it works, and let you know what I get. All right, so if I evaluate that, as I said, I'll leave it for you to do. I did it, but I just don't want to write it all. I get negative pi over 4. All right, so that's one way to do the problem. That's the direct way. Now let's try doing it with Stokes' theorem and see if it's any easier or any quicker to do. Hope so. Let's give it a shot. Okay, so Stokes' theorem says if I have any curve, and I'm in 3D here, and it's a closed curve, positively oriented, then the line integral equals this, which I like to just actually say what it is. It's the flux of the curl. The book writes it this way. So flux of the curl. And the way that I like to do integrals, flux integrals, is that shortcut we learned where we take our vector field, in this case it's the curl vector field, and we dot it with the gradient of g, where g is the way that I described it, and I'll do it here in a minute. That's the integral that we have to figure out. I went ahead and found the curl of f. I'm sure that you can do that for this f, so that's the curl. And I'm going to then need to know what g is and what this gradient of g is. So g is, well, good question. What is the surface? We can use any surface that is bound by this curve. So we could use this blue surface, that's the paraboloid, or we could use the green surface, that's the plane. Either one works fine. The plane is going to be the simplest, so that's what I'm going to use for the surface. So the surface that we're going to use is the plane, surface, z equals x. If I get everything on one side, that's what I've been calling capital G. We'll need the gradient of g to get our normals. So partial here with respect to x is -1. Partial with respect to y there is 0. Partial with respect to z there is 1. This is supposed to be 1 if I've done the shortcut correctly. And these are upward. And do I need upward? This said that this is counterclockwise, which would be positively oriented. So I need positive orientation on the surface. So that's my g. The dot product then of the curl and that gradient, this dot product right here, is, what is that, -1 plus y. So we just have to get the double integral of -1 plus y dA. That looks easier. What is our d though? That's probably the hardest part of this problem, is what is D? It's the projection down here. And actually, we looked at that already. So this is that projection, and we got it. I mean, we see it from the picture, of course, but we actually got it algebraically a few slides back. And we found that it was a circle centered at 1/2 0 with radius 1/2. So this was 1 and the center was 1/2. It was x minus 1/4 squared plus y squared equals 1. So we found that earlier. That's our D. Then we need to integrate this over D. And we can do that a few ways. I mean, we could solve for y. Y would be plus or minus radical 1 minus this. So we can go from bottom to top there. And it's not quite as bad as it looks, because when I do this part, I'm going to get a y squared over 2. So that square root can go away. Actually, I could do it that way for you to show you it's really not as bad as it looks. But there's a more clever way to do this, and it would be a good review for us on our polar coordinates. This is not a circle centered at the origin, obviously. And so it's not a simple polar curve. But depending on your polar curve experience, you might recognize that this is one of those circles. In my class, I call them an off-center circle. It's a circle that goes through the origin, but it lies on the x-axis. And we learned that circles of that form have the equation r equals 2a cosine theta. Not that you need to have that memorized, but maybe it just comes to mind that, oh, this is one of those special circles that has an easy polar equation. If you remember that and you know that well, you can jump right to the equation. But if not, then the way we would come up with that equation is something on the lines of this. We got the equation, the one that I just erased, we got it by taking our paraboloid and our plane and eliminating z. We had x squared plus y squared equals x. If I convert that to polar coordinates, x squared plus y squared is r squared, and x is r cosine theta. That would mean if I divide by r is not 0. R is not identically 0 on this whole circle. R equals 0 is just the pole, the origin there. So r equals cosine theta would give me this circle. If you remember this formula, r radius is 1/2, and that is what that a value was, so you could have jumped there directly. Okay, so that circle is r equals cosine theta, and it is traced out, though, not from 0 to 2 pi, but from 0 to 2 pi. When I put in 0, I get 1. And then when I put in, for instance, if I put in pi over 2, I get r equals 0. That would be here at pi over 2. And when I put in pi, r is negative 1. So I'm pointing that way, but r is negative, so it's back here. So that's being traced out. All right, that's you probably would have to go back and review polar coordinates so that you could remember all that. But that's what I would do. I would switch to polar. If I did that, then I would have negative 1 plus y. Y is r sine theta. dA would be r, dr d theta. R is going to go 0 to that curve, and that curve we called cosine theta. And theta goes again, be careful here, it's just 0 to pi. It's not 0 to 2 pi. 0 to pi, in this case, will take us all the way around. So 0 to pi. Okay, so that one has no twists and turns in it. That's an easy integral. I'll leave that for you. For those of you that are interested in, if I had never seen that and didn't know what to do with that, how could I do this without switching to polar? What I would do if I didn't switch to polar is I would break this apart into two. So negative 1 dA plus y dA. This is just going to be negative times the area of this circle. So minus pi r squared. And this other one here, we'd be going from the bottom circle of half the circle to the top, and I erased that equation, but let me just put it back up here. Now this is what we found earlier. So I solve for y, get plus or minus, so the top half and the bottom half. So this part of the integral, give myself some more space, is the integral of y dy dx, and y I'm going to have go from the bottom half, so minus radical 1 minus x minus 1/4 squared. It looks terrible, right? Radical 1 minus x minus 1/4 squared, and x goes from 0 to 1. And it looks horrible, but because in this step you're going to get y squared over 2, I'm not writing this all out, just you could try it if you want. You're going to get a y squared over 2, so you're going to get the over 2 part. But as far as evaluating this at y squared, that's going to take care of these integrals. So you're going to get a 1 minus x minus 1/4 squared. And you're going to subtract what you get when you put in this into that y squared. Now when you put this into the y squared, it's going to become a positive. You're going to get the same thing that we had before, which I should have seen coming. That's 0. And as I said, I should have seen that coming, because when I see an integral that goes from minus a to a, if you will, these are the same but opposite, and this is an odd function, that's always going to give me 0. So that part is all 0. That was 1/2 times 0, so that's all gone. So what's left is this, and that is minus pi over 4, which we got the other way, the direct way, and we would also get here. If we had stuck with that, that was not a hard integral there. And this turned out that this wasn't either, but it looked like it was going to be. So now we did the problem 3 different ways. We did it directly, that was a pretty long way, and then we did it Stokes' theorem, but integrated 2 different ways. Okay? So that problem took a while to think about. Thanks for asking that question. I hope you learned something from that.